There we go. So welcome back, everybody. Today, we're going to start with our second practice session, which now we are recording. It's going to be led by Nicolás Loaiza, who is a senior PhD student here in IFIC, in the Institute of Particle Physics of Valencia. And it's going to be about going beyond the simple scenario lambda phi to the fourth that was already presented by Paco yesterday. So, Nico, the stage is yours. Please go ahead.
And thank you very much for the introduction, and welcome everybody. Good morning for the ones in Europe, and good afternoon for the ones in the other side. So let's begin with this. As Danny mentioned, we will now do a practice session about using again CosmoLattice, but maybe we can go now beyond the phi to the 4 theory that was presented yesterday by Paco. And let's play with this kind of potentials that maybe you have heard of them, maybe you have seen, or maybe not. And these are these hyperbolic tangent potentials, which I will just give a little motivation of why would us care about this kind of potentials. So, for example, let's focus on the choice of the exponent fourth for the potential. And these have the characteristic, these potentials called alpha attractors, that for large field values, phi much greater than the scale m, this approaches to a plateau. So it's a flat potential, and which is basically what we want for inflation, which is a slow rolling field. But making this choice of this function, we make sure that for sufficiently enough field values, large enough, I mean, we will have this plateau. And as the field value decreases, it will start rolling down the vacuum of the potential, the steady state energy state. So once we reach this vacuum state, the inflaton will start oscillating, as we already know. This will introduce us a nice phenomenology. For instance, also this kind of potentials have the characteristic that if we just expand them around the vacuum, the minimum value, it will have a very nice form that we already know, which is the lambda phi to the 4. So at the end, it's just basically the same potential, but with some much more nicer functional form. And maybe we can now make the relation of what this lambda scale here is with the lambda we already know from yesterday. And here you can see how we get it from the potential. And now there is something very interesting happening here, and that's why we will use lattice simulations, which is if we just simulate along the inflaton and we make it oscillate around its minimum, in principle, we have just a homogeneous background oscillating coherently. But if we allow them to evolve in a lattice, we will see that also the fluctuations of this inflaton field will somehow couple to the homogeneous background and will have an equation of this form. And if you already know this, this will lead to a parametric resonance. So we can follow this parametric resonance in the lattice, and we can even see what will be the back reaction of the fluctuations into the homogeneous background. And that's why we will use lattice simulations to study these kind of effects. So let's try to implement this in CosmoLattice. So the first thing we need to know is which are the program variables that we are going to use.
Oh, sorry.
We already know that we have.
Oh, sorry, can I make a comment? I mean, yes. Technically speaking, I mean, of course, we study in the lattices because we want to study the fluctuations, but in the linear regime, this can be studied also outside the lattice, okay? This is very important. The lattice, we need it because the system is going to become nonlinear, but the initial parametric resonance is a linear process and also can be studied out of the lattice.
Yeah, sure. Yeah, that I will make sure that we see that we need also the nonlinear part, which is what the lattice gave us, and we will see this in our results. But yes, that's true. The initial stage of a parametric resonance is a linear phenomenon.
Process can be studied out of the lattice. What we really need the lattice for is to capture the nonlinearities, you know.
Yep. So let's try to not to guess, but try to infer from our potential and from our model what would be the program variables that we need to implement in CosmoLattice. So for F star, there is a very easy choice, which is just using the initial amplitude of the inflaton. So as we want to capture and study when the inflaton starts oscillating around its minimum, we will start it right before the start of oscillation, so right after the end of inflation. So if we just solve or Klein-Gordon equation together with the Friedman equation for a single field, a scalar field, we can do this for the homogeneous background. We can do this in mathematics or whatever choice we do, and we can find which will be the field amplitude at the end of inflation, and this will be our choice for F star, which is very easy to guess. And omega star, what will be? So it's another easy choice for us because omega star is some energy scale, the like relevant energy scale of our model, which could easily imagine that it will be like the oscillation of frequency of the inflaton, or in this case, this effective mass that this potential has. And if you just expand this around the minimum and then to take the second derivative, you will see that our choice of omega star should be of this form. And this you can actually do for any exponent I put it here. You will find that something similar will arise. And what should be alpha? So alpha is 1, but I encourage you to check what it should be 1. I think this already was explained yesterday, but if not, I encourage you to check why we choose 1 for this case. So now that we have our program variables, I will just write down my potential in its program variable. So as you remember, for the potential now we have to normalize this by omega star square and F star square. And I guess there is a typo here because I'm missing a 4th power here. Yes, I'm missing a 4th power here. Sorry for the typo. And then basically what you should do now is taking the derivatives, the first derivative respect to the field and the second derivative respect to the field. Okay, and now what we should do now is to start writing down our model file. So maybe now if you have any question now about the setup before we jump to the writing of the model. Is there any question? No. So maybe what you can do now, because this is a practice session, you can try to write it down yourself. In the public version, there is no implemented this model. So maybe you can do yourself in the meantime. Can we proceed like this? Like people write down their own model file for 5 minutes or 2 minutes? Is this okay?
Sounds good, Nico.
Can I have some feedback? Okay. So maybe if you already download CosmoLattice, you will see that in the models. Let's go now. I downloaded CosmoLattice myself yesterday. And you can see that there are these models that are implemented, and you can try to write down the Tanch PP4 model. So please tell me when anyone has done this. And maybe we can then go through the one that I wrote myself. And maybe you have any question again regarding the potential or why I make these choices, you can do it now. Okay. So please tell me if anyone achieves to do that. So, anyone
Maybe you
want to
want
tell me?
you want to show the model file, Nico, so they see.
Yep. Yeah. So okay. So maybe what you should have done, which was the easiest choice, was to actually open the tangpp2 file, copy paste to another new
PP4.
file. The tang. No, I mean, so what we want to do is to create the tangpp4 one.
Okay, I see.
So we just make use of the one that is existing because that's what we want we want you to do, because it's we don't want you to write this from scratch. So the idea is you copy paste from an existing model file and start editing it. So maybe we can already go through. So what do we have to take care about? First, changing the name here, make sure that the name is a new one. Make sure that now the number of scalars and the number of potential terms are the ones that we want. And why I am choosing 2? Because we are actually, I actually want to do something else. And I will explain you now. I actually want to also consider the coupling of the inflaton to a Doppler field. And now we will have this kind of excitation, not just of the inflaton field, but of the Doppler field as well. So that's why I choosing here 2 number of scalars. Why 2 number of potential terms? Because I have the potential of the inflaton itself and the interaction term, which is given by this kind of interaction. You can choose whatever you want here, of course, respecting some symmetries, but you can choose whatever you want here, the interaction term. Later, what should we do care? We should care about putting the right name here, and this name should be the same as the one that we're going to call this file. So if this file is called tangpp4.h, the model name here should be the same. You should make sure of this because otherwise it's not going to compile. Then we should declare our variables, in particular the constants. The program. How are we going to measure the program variables? So for example, you remember we have the m scale, we have the lambda to the 4 scale. We will have the initial field amplitude, the omega, the q, which is what I will call it the resonance parameter, and the g, which is the coupling between the Doppler field and the inflaton field. Then in this part, we are telling the model that we want to extract from the parameters files these numbers. So whatever I call m in the parameters file, it will be assigned to the m that I will be using here. The same for lambda to the 4th, the same for the resonance parameter. Now I am telling here that the whatever is called initial amplitudes in the parameters file is what I will introduce it as for example, the initial field amplitude, and the same as for the initial momenta or the pi, the conjugate momenta that you know. And then I am declaring that my phi star, what I call f star, is the initial field amplitude of the inflaton. My coupling, I will read it from the resonance parameter Q here, and I already spoil you what should be this question here. What is Q, the resonance parameter? Q will be what it remains once you take this potential and convert it to program variables. You will see that now we have to divide this again by f star square omega star square. We will have here that term that I already showed you, and here we will have another term, and whatever remains here multiply times the chi square phi square in program variables will be what we call the resonance parameter Q. And this is what it goes here. And I define what will be my omega, which is lambda square divided by m square times phi star. Now I am saying CosmoLattice choose alpha equal to 1, which maybe I should ask this. What was alpha equal to 1 in CosmoLattice? It is coordinate time, conformal time. Does anybody remember this?
Conformal.
Hey, nice. Yeah, conformal. So, and maybe do you know why we choose conformal time for the 5 to the 4? Well, this is the clever choice, and this is something that maybe you should check yourself. But yeah, the clever choice for lambda 5 to the 4 or from the tangent 4 here is the conformal time. And finally, we just write down our potential terms. So you see, I write down my inflaton potential energy and the interaction energy, and you see, I just exactly do what I show you. This is the missing fourth power that I was missing in my slides. It is here. That is the interaction term. Now, instead of the g squared, because now everything is in program variables here. So instead of the g squared, there is the q, the resonance parameter. Now I write down the derivative with respect to the inflaton. I have this first derivative that I show you in the slides, plus the first derivative related to the interaction term, the same for the Doppler field, and again, I write down this. So has anybody achieved this by themselves? Do you think you will be able now to compile and get the executable for this model? Yep, is anybody doing this? Tell me if you have achieved this.
Is anybody finding problem in doing this? And if so, what's the problem?
So maybe once that you have write down your model, we should go back to where CosmoLattice is. You already did this yesterday, right? So here I already create the build folder that we are used to, but actually you can call this whatever you want. So let's create another directory, call it build 2. No, let's call it tang p4, okay? We go into tang p4, and if you have everything set, this will be easy as doing cmake. So yeah, let me do this the model. Now here it will go how you call your model, which is tang pp4. And
let me
remember this.
1 second, Nico. I mean, let me
Yes.
ask those of you who have prepared the file, if you've managed to follow the real-time instructions, can you raise up your electronic hand just to know that you are there? Or shall we really, assist you in writing the file?
Or address any question, yes.
Yeah, there was no difficulty, but it was a bit quick for me to. I mean,
sorry.
You went through the file super quickly. There was no time to copy.
Okay. So let's go again. Yes.
Let's go again slowly, please. Yes.
So again, let's start from the beginning. So we took one file from the ones available. We just copy paste and start editing it. Okay. So we went through, make sure we have the right number of scalars, the right number of potential terms. We define our program variables, also what we need. We make sure that we will call from the parameters file the program variables we need, or the constants that we need. We make sure now that this is super important here, that you make sure that you choose the right alpha time.
Maybe something you can do
sometimes
is like for other people, this is really modifying the potential and the potential derivative that just take time. This is just a simple but take time. So maybe you can also what is the difference compared to the original file, so that we do not miss any modification.
So yeah, the original file will be any file that you copy paste from. So if you choose
I meant the one with the tang p2, yeah.
Yes, if you choose from the tang pp2 one, that you will. So what I will do in this case was go into slides that are available, checking that especially these powers here are the ones that will change. So it's instead of 2 will be, now it's a 4, here's a 4, here's a 4. This is the ones that you should make sure that you change.
Nico, some people are asking for the PDF for the expressions in your PDF of the derivatives, but maybe I think it's okay. We show them here, no, like this, and I'm referring them to the PDF.
So yeah, there is I mean, there is not a typo, but there was some weird representation of this in the PDF that is available at the Indico page. But the expressions that are there are fine, except for the missing fourth power here. So make sure, I'm so sorry about this, there is a missing fourth power here. And so there is something that you should forget while implementing CosmoLattice, the sign function here. This is something that is put in there when you do the derivative, but in CosmoLattice, you don't put this here.
You don't put it for p equal 4. Yeah.
Yes.
Isaac Schoenberger is writing in the file, can you send the model file to use as a reference? And I would agree, because if we just grew up with missing one power, then we will not be able to follow afterwards.
Yes. If you miss one power, it will, for sure.
So Nico, can you pass me the file maybe through Skype or somewhere else, and I upload it in the material of the schedule, so they have it?
The new one.
The one you are asking them to implement with the final thing.
Oh yeah. I mean, sure. I mean, I can do that. Sorry if how should I do? So let me. Okay. I know. Should I open the Skype from here? I'm so sorry.
If you want, yeah.
Yeah. I will just do it. Can I do something like this here?
Nico, perhaps you can also upload it to the Zoom chat. I think it's possible.
Yeah. Can I do that?
I don't know.
So
what are you proposing?
How should I do that? It's through the messages?
I think you were already in Skype about to pass it. Please just pass it there, and then.
Okay. I just do it here. Okay. Okay. So I have it here. So I have it. I will pass you this and also the model file. Okay. The parameters file and the model file.
Thank you.
I will pass to Danny, and Danny will upload it to Indico, or maybe here in the chat.
I will do it in Indico, so it's there forever, and people can take it from there. If I put it in the chat, we lose it when we close the chat.
Okay, so I will go now here. Who is in this step? Is anybody in this step the one?
If raise up your electronic hand in order to answer positively this, yes, please.
So okay, nice.
Only 3
so
people.
Like there is people that have achieved writing it, a model, and also compile it. So make sure that you compile by doing make CosmoLattice. So this you will make sure that at least there is no problem in compiling the model.
Nico, but few people answer they are there, so we may want to assist.
Okay. So
the rest of the people to still write the file or take it from the schedule. If you give me a second, I'll do that.
Okay, so I have it mine compiled, but let's wait for the people. So I will show you again the potential terms in the model file, or the one that it's already in Indico, I guess.
Yeah, you have them in Indico now, guys, if you just want to take the file directly from there. Or just look at the file while you try to modify your own file, which would be the best practice, of course. Kursit, is this a question or you just left your hand up?
Yes, yes, I have a question. Yes.
Go ahead.
Yes, please.
Okay. So for tan hyperbolic model, model, this potential has a inflection point. Okay. So how do we choose the parameter file then? First question. This. So can you give this answer?
Sorry, I didn't get it.
There's an
Can you
inflection
repeat the
point.
question?
And what is
Inflection point. Yes.
Yeah. And what is your question about it? Sorry.
How do we choose the parameter file to avoid the inflection point first?
Okay.
And
so
yes. First question.
yes, sure. So this is a very nice question, because in the tangent potentials, the hyperbolic tangent potentials, there is this thing that happens that when the inflaton rolls down, it will go through a inflection point, of course, because there is a change of curvature. So here, this is something I will show you later. Okay, maybe I can show you already the parameters file that I have it here. So how do we make sure that we do that? So for the case of this is you can show this for in a general case, that for this kind of potentials, you can compute what will be the inflection point. And for example, if we choose that we start our simulation at the end of inflation for this choice of M scale, which is 10 times the Planck mass, we make sure that we are starting our simulation below the inflection point. But this is a particular case. For the case of M, this mass scale equal 10 times the Planck mass, and choosing the initial amplitude to be the one at the end of inflation. And what do I mean to end of inflation is when I solve the Klein-Gordon equation for the inflaton, the homogeneous one, in mathematical, let's say, the end of inflation for me is when the epsilon parameter for the Hubble rate, the minus h dot over h squared, is equal to 1. This is my choice of how to choose what the end of inflation is. I do that in mathematics. I compute what is the initial field amplitude, and in this case, I can also show that for M equals to 10 times the Planck mass, I am starting below the inflection point, but this is not general. So for example, if you choose M, a smaller scale, like 0.1, the Planck mass, and you also choose the initial amplitude to be the end of inflation, then in that case, you are not starting below the inflection point. So this is how you choose
what will be the yes, I understand, but what will be the problem if inflation end at the negative curvature? What will be the problem for if I
well,
is there any problem to simulate?
No, well, the simulations just go through. I mean, of course, you are now introducing some stages.
I am starting.
I mean, are you worried about maybe formations of oscillons? Maybe are you worried about that?
No. I am asking if let's say you are considering a small value of M. Okay, so our inflation will end at the negative curvature. So what will be the problem if inflation end at the negative curvature and our simulation start from the negative curvature? What will be the problem in our simulation? Is there any problem, or we will get the correct answer?
No. There is no problem. You can do that. You can do that. Yes. I mean,
but
if you are.
But I have run the code. They are showing some error. In not error, they are showing some message. They are seeing message like you are starting from the negative curvature and your equation of motion is choosing only k. They are not considering the mass term of this negative curve. So they are showing this message. So when I
yeah, I think what you are describing is that you are starting in such a stage that the effective mass induced is positively, so the square of the effective mass is negative, And
yes,
then,
yes, yes.
And then the vacuum fluctuations expression for initial condition we use is not valid a priori. Okay, because the expression we use is for stable masses. Okay, so essentially the way to solve that, whenever you encounter such a thing, is that those masses that turn negative should turn negative only dynamically. So you should always start whenever you have the positive defined mass.
So is there any problem if I start from the negative mass?
The problem is that the expression for the quantum vacuum fluctuation is not valid. That's the problem. And there is no clear expression to plug there. So you should start.
Yes.
I mean, what other people did in the past is they were removing the mass square term negative in the expression of the fluctuations, and then they were leaving only the momentum. If you are dominated by momentum, then it's not a problem. But we decided to put that flag because if you accidentally start by negative square masses, probably if the masses weigh too much compared to the momentum, you are faking the initial conditions, you know, of the fluctuations. So you want to avoid starting in negative square masses. You want to avoid that. You want to start in positive square masses and let the system flow into negative square masses.
And after when field oscillate around the bottom of the potential, then if it is again positive, so it will handle then it will handle the positive mass square, or your equation.
This is only for the initial conditions, what I'm saying, okay?
Okay.
Initial conditions require you to set up the homogeneous amplitude of the field and velocities, but also there is a spectrum of fluctuations. This is where the problem comes. In the spectrum of fluctuations, there is an expression for quantum vacuum fluctuations, which is only meaningful for positive defined square masses, okay? What happens afterwards if you start with positive defined square masses? It doesn't matter, you know, the dynamics will take care of it later on.
Yes.
But if you start with square masses which are negative, it can be problematic conceptually, and that's why we put the flag to rise up the concern, you know, that you should be aware, and you may want to modify your initial conditions.
Okay. So,
or my recommendation is you start in a situation in which the square mass is positive, and then if it turns negative later on by dynamics, this is irrelevant. The important thing is initially it's positive.
If I consider those modes which are greater than the negative mass square, then this will then our code will run correctly.
No, I think currently we put the flag to stop you and let you see that you have that problem. Then if you want to remove that flag, you have to go to the code to initial conditions and remove that, you know, so you let it run at your own risk of whether that is correct or not.
Okay.
Please,
Okay.
I mean, how to say? CosmoLattice can be used as a black box, but when it enters into a situation like that, then you have to start thinking, what is your physics? What do you need to really set up for your initial conditions? And then you might need to modify the spectrum of your initial conditions, or remove that flag. And if you are happy enough because k squared dominates over the negative mass squares, then up to you if you consider that as a good expression for the fluctuation. Okay. In my opinion, or in my experience, what I typically make sure is that I start in a situation where my fluctuations are guaranteed to be well defined, the positive of the mass square, or at least I'm well inside the Hubble scale such that k squared dominates sufficiently, and then I let the code run. And then if the dynamics becomes tachyonic, that's fine, you know, but you should start from a good initial condition for the spectrum, you know. Okay. You need to look into the code inside. It's not as trivial as just, you know, can I run or not, you know, and think about your physics.
Okay, now you have to think about fields, not about the numerics. If those modes which are greater than the negative mass, then we can get the correct answer. We have to think about the physics, which mode we are working.
Yeah, I mean, if the modes, if the momenta are larger than the negative mass square,
negative, yes, sir.
You may want still to your code to run with the standard quantum vacuum fluctuations expression, but that doesn't mean that is correct, you know.
Okay.
Because you are taking an expression that is meant for positive defined square masses. So, you know, probably it's more or less correct because you are dominated by k squared, but how incorrect it is, I don't know, you know. That's where you need to understand your physics. So if you remove the flag and let the code run, it's not guaranteed that you are doing the correct thing.
Okay. So,
Sorry,
is there any possibility to remove this unambiguity? How do I? If I, let's say, you are in the negative curvature, then you have to put the correct vacuum for this negative curvature. Then.
Yes.
Without putting correct curvature, you are not able to do any simulation for the spectrum part.
It's a problem of you understanding what is the physics you want to simulate. Okay. So if you want to simulate a situation where effective square masses develop negative, you need to understand what's the spectrum of your fluctuations. So one possible solution that I'm telling you is you can start in a circumstance in which the square of the masses are positive, and then you let the dynamics run into them turning negative or whatever later on. Okay. If on the contrary, you want to start a priori from a situation in which your square masses are negative, then it's up to you to understand what is the spectrum of your fluctuations, you know.
Because same case is happen. If you see, the same case is happening for the hybrid inflation also. Hybrid inflation first initially it is positive curvature, but later time it has a negative curvature. So same thing is happening for the also hybrid inflation.
It happens in many scenarios. I don't.
Yeah, many scenarios. Yes, I have given another example. So that's why.
But you understand the prescription I'm saying.
Yes, I got it, but I have to think on it. So
I think you need to think about your physics, and also I think you need to go into the code now at a deeper level with the manual and see where that call to initial conditions is, and then decide what you want to do with them. And I'm already giving you an idea. Typically, starting the dynamics when they are positive defined, and then let them run to become negative or whatever.
Okay, I got it here. Yes, I got it. Your answer. Now, first, I start from positive and let them to feel the positive, negative parts. I got it.
Or if you know what is, for whatever argument, analytic or other, what is your spectrum of fluctuations when they are negative mass square, you can also modify that functional form in the code, you see?
Yes.
But you need to know that, and to my knowledge, that's not easy to know. Okay, I think
there was another question.
Thank you. Yes.
Yeah.
Seb, you want to ask?
No, sorry. I mean, I had a technical problem. I solved it. I have another one, but it will slow down people. It's okay. I mean,
no, but it's fine to ask the technical problems here. This is session of.
Okay. Fair enough. So initially, I was just compiling, and it was saying me dt is unknown, and actually, when I opened the file with parameters dt,
no, it's because
there was the question mark, so I changed it.
So the question mark was people.
Fair enough. So I opened another one. I took another one. This was solved. Okay. Second stuff, when I run it, there was, and then, okay, maybe it's annoying for people. It was not able, it was writing could not open test average scalar 0.
It was because, I mean, I wanted to, because there was the output file, I chose it because I wanted to show you what was done, but
sorry.
So so that means that everybody, I mean, is everybody has compiled the model so far?
So compiling and not running, right?
Compiling. Compiling, because not running, because then the next step was going to ask people.
Okay. You made
what
mistakes.
Is the DT you should choose here? And then the other thing was that usually something that what I do, what I am, is in the build file that we created, I like to create where it goes my output, so I don't have it all the output in the same build file. That was everything. So I just create another directory in the same folder that I build my executable, and that's what I call it from here. And that's maybe if you start using CosmoLattice, that's something you will going to do, that you will actually choose an output file here, so you know where your output goes. That was all. Okay. So yeah, so I just leave this question mark here because I already chose for you what should be the k-infrared and the number of points. So that means that you already know what should be your dx, your length of the box, and also the dx, which is the smallest length in the box. So according to this, which detail should you choose? And that's why I leave this question mark there. So maybe if you choose correctly your detail and you run the code, you should be able to get the results by yourself.
Can I ask you raise up your electronic hands, those who have managed to compile? And don't remove it, please, so we can count a little bit.
So now, okay.
So half, well, not the half, a third has managed to compile, the other third, the other 2/3 not really. Okay.
So does anybody have a problem while compiling? Could tell us if there is some error or some flag that appears while compiling?
Yeah.
That you would like us to answer this?
You can lower your hand, those of you who managed to compile, and then those who are trying to compile but are having some error, as Nico is asking, do you want to ask out loud or comment on the error or problem, please? Sure. No. Okay.
Okay, so let's and then for those who were able to compile and now were able to even run the model and also got results, which DT did you choose? Could anybody tell me this? That one, does anybody want to tell me which DT should I choose?
In the chat, they are telling you, Nico.
They are telling me in the chat. So we can choose, okay, well, maybe the DT 5, 10 to the minus 40 is very small. Which will be the largest DT that we can choose? Do you remember how to do this? So, okay, 5, 10 to the minus 4 works, but maybe it's too small. Okay, when I run, I got an error. Okay, so that means that in your parameters file, Sidalu, that you are not giving it the number of points per dimension. So maybe if you see the parameters file that I uploaded, or that it's in the Indico, okay, the DT should be smaller than 0.17. Okay, that means that, okay, just for having nice numbers, I can choose DT 0.1, for example. Okay, so let's try with the 0.1, no?
Oh, Nico, by the way, we've been over 45 minutes. Do you want to make
okay, so maybe in this time that we can have a break, and then when we come back, you have time to compile yourselves, and we will be back to just now looking at the results.
Excellent, thank you.
Just a quick question: if you want to quit the code because, for example, I launch it with a too small time step, how do you do it properly?
I do Control C in Mac. Okay, and that stops the code running.
Control C is a general set of commands for canceling it in your console.
To cancel any execution of any program.
Or command dot also should work, I think, in Mac.
I do have an equal 32 in the input file. Make sure that is not commented out, maybe. Okay, so if you go, yes, maybe that's what the friend of Paco says. Maybe that's the problem, that you are not calling the correct one. So so for those that are here, maybe I can, once we have everything done, I should do MPI run. No MPI run, just.
Nico, we are in the break anyway, remember, okay? So let's not.
Okay.
Let's wait, please.
Let me just do myself a little test. Usually when I do this, I always do MPI.
Sorry, may I ask another small, very naive question?
Yes.
Previously, I had launched it with a small time step, and so I interrupted it. I launched it again with a more reasonable time step. It seems to work, but it finishes in 1 second, and when I open the txt file, they are empty. Do you have any idea?
Empty.
What, yes. I know it's hard to imagine if you're not in front of the computer.
Okay, let me see. So, for example, I just did some test myself. Call it bunch people. And see, why should I?
I had no errors.
And the parameters file that you are using, like it's something like this that I am showing.
Right, I think I took 0.1 for DT, but
okay, so the 0.1 I was trying to choose and it didn't work, so maybe it's slightly smaller than that. Try to use.
I try to do it. Okay.
Yes.
Thanks. I'll tell you.
And then, for example, because of the way the spectra file at this point should be empty, or at least should only have, yeah, the spectra files are empty because I told the program to measure it every 50 time units.
Yeah, we'll make
because
it
if you didn't wait very long, maybe this one is empty because it hasn't had time.
I think it was. I understand, but I think it was all of them. But okay, let me check with a small text.
Okay. Yes.
Yes, thank you. So my problem is that when I try to compile through make CosmoLattice, it says there is no rule to make target CosmoLattice. Is it
so
stuff?
okay, so you did a CMake first.
Yes.
And you got like this.
Exactly.
And then there is, in this point, there is no error. Could you tell that there is no error in these
No.
messages there? And then when you do that, it creates several files like CMake cache, all these files, some CMake files folder too.
Inside the build
yeah,
folder.
when inside where you do the CMake, like the build folder.
No, there is no file inside actually.
So when you do the CMake, make sure that so for example, here I am doing it. Maybe I can show you again. So let me, I just clear this. Okay, so maybe I am going back. I'm creating another build too. So you do CMake. I mean, I do this just because I always run like that. You do the model, right?
Let's consider we are back to the actual practice session, okay? Although there is not much of a difference, but yeah.
So yeah, I'm answering a question of somebody that didn't. What did I do? Oh no. Okay, so that's always important. Go to the folder, and then you can do that. So who was the question? Sorry, I forgot. Antonino.
Yes.
So when you do the CMake, there are some files that are created and some folders too. So inside of the same,
there is
yes. Yeah, tell me.
Yes. In my case, it doesn't create any file.
So maybe there is some issue with the CMake.
Antonino, but you have not run CosmoLattice before?
Yes, I have.
So this is a new problem you are getting right now.
Yes, exactly.
So
and
you make
exactly copied the file from the.
So you make sure when you call the model file that you are calling has the correct name and it exists in the model folder.
The model folder, yes, exactly. That's what I did.
And so that's why I told like you should call your model file exactly as the way you should then call it in the CMake. You make sure of this.
Exactly. That's what I did, in fact.
Okay, and then it does all this screen. It does the CosmoLattice screen. It goes through all these messages.
Not all of them. Not all of them.
Well, it's because I myself I have created. I have installed all the packages like FFTW, the MPI. So maybe some of them shouldn't. Like for example, the MPI shouldn't appear for you because you are still not using the parallelized. But the other ones, yeah, the FFTW should be there for sure.
Yes, I have downloaded the FFTY.
Okay, and still it doesn't create these files. Maybe, if you keep having this problem by the afternoon, so like in the afternoon, are we going to do this break through room, something like that, Danny?
Sorry, Nico?
During the afternoon session, like over the coffee break, are we having these break rooms that we split in groups, and maybe we can address these kind of questions by looking actually at the screens of people? Or
yeah, we can address them without necessarily splitting in rooms. This depends if there are many questions we split. But
well, maybe there is somebody that doesn't want to share the screen for everybody, but okay. Because this looks something that maybe looking at the screen could help. Because beside of that, I don't know.
It requires personal assistance by looking at the screen, so the user will need to share the screen. On the other hand, I think, yes, we can postpone. At this level, I think that can be postponed for after the lectures, and then we discuss that. On the other hand, Antonino, if you've run it before and compiled before, you should think what you are doing different now because something has changed, no?
Okay.
You have just changed whatever, and now it's not getting all the files where they need to be.
Okay, thank you.
And Sebastian, were you able to run it? And
yes, everything worked fine now. Thank you.
And now you got okay. Thanks. And then the rest of the people were able to get some output files with not non-numbers.
Okay, rise up your electronic hand, whoever got output files with no non-numbers.
So that means that you choose the DT correctly, at least, and that means, but okay, there is one issue here that, of course, we are doing this in our laptops. We cannot go beyond 32 points per dimension, maybe. And plus, I am sharing a screen using Zoom or using all the apps. I cannot go into 64. So let's all imagine, with the magic of production and edition, that we have our results. So let's go through them.
Let's one comment.
Let's imagine I did.
One comment is, let's clarify, it's not a matter you cannot do in your laptop 64 or 128, is that it would take very long, okay? And for the purpose of real-time demonstration, we don't want to do it, okay? But for the physics purpose, if you want to capture well this physics, you definitely need to go to a separation of scales at the very least in 60 points per dimension, most likely 128, if not 256, to have a good handle of the separation of scales, which probably means you need to run in your laptop for many, many hours, or to launch it into a cluster if you have access to one. Okay, there is a question. There is a question here, Nico. Do you want to answer it? How do we know whether the range of n is large enough? Do we just try it out?
Well, yes, basically, yes. So maybe if I go back to my slide a little bit, let's go here. So at least for the case of parametric resonance, you could tell from the linear analysis of this equation, like as Danny said, that we can actually follow parametric resonance, at least in the linear stage, analytically. And this could tell us, for example, what will be the initial band of momenta that will be excited. So this could tell us, for us at least, what should be our infrared. Okay, so if we know that we need to excite some band up to a certain value, then we choose small enough or infrared. We choose our cutoff here to cover that initial band, and we can start playing with the n number of points per dimension. So we set our infrared scale because we already have knowledge about what will be the initial band of momenta that will be excited through parametric resonance. And then we start just playing with the number of points per dimension, which in this case, if I set what is the infrared, by increasing the number of points, I am increasing the UV coverage. And because we don't know what will happen in the nonlinear regime, because that's something that the lattice will tell us, how do we know? Basically, a rule of thumb that I use is that our spectra falls exponentially nice in the UV, and I will show you some examples of what to expect when we are sure that our UV coverage is fine. I will show you some examples. So that's basically trial and error. So yes, you just try out what you need. So let's imagine I did a simulation of 128 points, and I have it here. So I just started with no depth field. So in my program, in my parameters file, I choose Q equal to 0. That means that I am not exciting the depth field. I am just doing the inflaton field alone. And maybe all of this you have seen already, but let's go through it. When you produce your results, you will produce several files. For example, there is one that tells you it has the information about how the scale factor evolves. And here I show you a plot of how the scale factor evolves with the choice of time that we make. And we choose alpha equals to 1, that means conformal time. And as you may know, or that's something you should check, is that for the lambda phi to the 4th theory, it will have a equation of state of a radiation dominated, like a radiation dominated universe when you have just phi to the 4 alone. And you know that in a radiation dominated universe, the scale factor scales linearly with the conformal time. And this is basically what I'm showing you here. Scale factor is scaling linearly with our choice of time, which is conformal time. And that, for example, that's something that you should check. If you have this knowledge that what will be my dependence on the scale factor to the choice of time variable for my problem, you should check that this is fine. Then I can also plot, for example, how the Hubble rate behaves. We can see that it decreases. And then some other interesting things to check are for example, the field amplitude, the average amplitude of the inflaton field. Here you can see that because of my choice of conformal time, the oscillations basically are well resolved. there is the initial fall coming from the end of inflation, that it starts oscillating. And then if you, for example, want to check something, that's something you could do, is that you can actually solve this and have the same result by just solving the homogeneous background equation in Mathematica, for example. You can put this on top of each other, the lattice result and the homogeneous background equation, and you can actually, you will see that this should go one on top of each other. Because initially, because I have just the inflaton alone, the homogeneous background will be the dominant solution. There are no fluctuations growing and nothing like that, at least in the first oscillation. So that's something that you could also check to test the validity of your results, for example. And then something that we won't see by just doing the homogeneous background equation is this, what is happening here. So now I am plotting the conformal field amplitude. I am multiplying times the scale factor, the field amplitude, the volume average of it, and we can see that initially it has the same, which is expected, right? The field amplitude just scales conformally with the growth of the universe, but then it starts decreasing. And this is a hint of the back reaction of the inflaton onto itself, like the fluctuations that will grow due to the parametric resonance will start back reacting onto the homogeneous background. And this is the hint that we are seeing here is the decrease of the conformal field amplitude. Okay, this is already a hint of not nonlinearities, but at least of the parametric resonance happening. And actually, no, yeah, this back reaction is already a hint of the nonlinearities that have kicking. Okay, so this is possible to see this in the lattice, this decrease of the conformal field amplitude. And then another way to show this is by checking at the conformal root mean square of the inflaton field and how it grows. And this is just due to the nonlinearities. Maybe we can see this, is that the conformal field amplitude starts like decreasing at 400. And here we can see that actually this root mean square it grows before, but it is basically very large already, like at this level at 400 here, but it already grow here. So this is a hint that the decrease of the conformal field amplitude is due to the back reaction of the fluctuations into the homogeneous background. We can also check at the energies, for example. Initially, of course, we have the kinetic and the potential energy dominating it and oscillating. So one oscillates and the other takes over and like that. And then at some point, the gradient will increase. And again, this is a hint of the first parametric resonance, growth of the fluctuations. And at some point, when it achieves 400 here, the gradient energy is a relevant fraction of the total energy. And at below 400, we see that it's already on the level 10% or well, 1%. At this level, maybe 10% of the total energy. And this is only it's only possible to see in the lattice, this growth of the gradient energy here, and how the back reaction of the fluctuations modify the homogeneous background. And here I show you the power spectrum of a scalar of the inflaton field, the mass power spectrum. And this is a very nice plot because something nice about the 5 to the 4 theory is that it creates these features in the power spectrum, this spike here, because the parametric resonance is such that it probes just finite windows of momenta, and that's these excitations here. So this is due to the linear regime of parametric resonance, the spikes here in the power spectrum, but then because of the nonlinearities, there will be now communication between modes, and it will start actually flattening this curve and actually also pushing power to more UV modes. And this is what we ended with the blue curve, how it's very flat or spectrum now, power spectrum. And this is already due to the nonlinearities that are only able to, we can only capture in the lattice. We can also see, for example, the occupation numbers. Again, we have initially that the growth of the occupation are only happening for a window of modes. It happens again also in this window of modes here, and this is the spikes that we can see here. But then again, the nonlinearities now start populating modes beyond these windows and do even more UV modes. And how do I know that I did a good choice of my N? Is because I have this exponential fall in the UV. So if I were to, if maybe you check in your results and you plot the same, for example, the power spectrum of scalar fluctuation of the inflaton, sorry, you will see that in the UV there is no this fall, but actually maybe it grows even in the UV. That's a hint that, or that shows that you didn't choose correctly your UV and you need more UV coverage. You will make sure only that your UV coverage is good enough when you have a exponential fall of your UV tail. And this will answer the question of how do we choose our N. Basically, this is how you choose your N. In this case, you have your exponential fall in the UV tail. And already spoiled something. And maybe, is there any question up to this point that you would like to ask?
There's a question there. I see one hand up. Yeah.
Yes, please.
So can I ask you? Yes. So can you go to the spectra plot?
Yes, this one here.
Yes. So what is the value of this mode in terms of Planck, in terms of megaparsec? I want to compare this mode as compared to CMB actually. So
but these are the
how much large
spectrum.
How much large than the CMB this mode?
So these modes are much shorter in wavelength than the
shorter,
CMB.
yes.
This is
I'm saying
so these are modes
in terms of K. How much
so,
large compared to CMB?
I'm answering to
what are yes.
So these modes are way much shorter than CMB scales because they are produced after inflation, okay, and they are sub-Hubble after inflation. So they are 60-fold separated away from CMB scales. But if you want the exact number, what you have to do is you see that K tilde that Nico puts there, that represents the comoving K over the omega star Nico chose, okay? That omega star has dimensions, and hence you can represent you can represent it in GeV or in inverse megaparsecs if you want, So you have to translate that scale into whatever other unit of comparisons you want to have,
So is this large mode affected by this negative curvature of this tangible potential? Is this large mode? I'm saying this because this mode is too large.
Well, no, as I say that these are shorter. This is short scales.
Length scale is shorter. I'm saying mode means K. I'm saying K. K is too large.
The large K.
Large K, yes, sir. So is this large K affected by this negative curvature?
By affected what by that?
But the negative curvature of the inflaton potential, you mean?
Inflaton potential, yes.
Okay, so in this case, I choose my parameters such that the inflaton does not go beyond the inflection point. So in this particular case, it just oscillates around the minimum, and it just oscillates around the positive curvature part of the inflaton. In this case.
Yes, this case I know, but if I am saying Is this mode
if I were
when
to, I don't know. I should. That's something.
I don't understand your question. Sorry, Kursit.
yes.
Nico
So I am
has
saying
set
yes.
the initial conditions in a situation where the vacuum fluctuations are positive square defined, and then it follows the dynamics.
Yes, but let's say I'm starting from the negative curvature, and I am giving the mode which will be excited this mode when this range of this mode which we have plotted here. So then it will be create any problem.
There isn't. If you do things consistently, as I'm telling you all the time, there won't be any problem, and you are capturing well the physics. You just need to do it consistently.
Okay. Thanks.
You just need to understand this yourself, Kursit, because
my answer will be try yourself, because
cyclical in telling you the same answer.
that's something we haven't explored for at least here.
Okay.
If you want to know what's the dependence on the UV scales
Okay.
to the curvature
No, but there
of the
is
potential.
The physics is well captured here, okay? The physics is well captured here. So the point is, if you have a situation in which your modes turn into tachyonic, this is going to be well captured as long as you have started with positive defined square mass modes. And otherwise, you need to provide the prescription yourself as to what is the initial spectrum for those tachyonic modes if you want to start in the tachyonic phase. But for this choice, everything is consistent. There is no problem. We are capturing well the physics.
Okay. Thank you.
Okay. There was another question. Okay, I think Paco is addressing them. Okay, so maybe another question about this. So okay, maybe something I didn't say, that of course whatever I am plotting here is in program variables. So always remember this. So if you want to get like physical results or numbers with units, you should know how are we measuring this and multiply by the relevant factor that you need. For example, if you want time in cosmic time, you should multiply this by omega star, or yes, and then convert it to cosmic time or conformal time. But all of these are in program variables, all these results. Okay, that's why it has these numbers. Okay, so maybe
Nico, sorry. I think so. I have tried to address this question, but I don't know the answer. So I think we can discuss about this in general. There is Ricardo who is saying that the spectrum is 0 for each mode, even under the cutoff of the initial fluctuation. And I think that should not happen, right? It seems like he's saying that it seems like perturbations are not initialized at all. But of course, they should be populated, right?
I mean,
so I don't know if any I don't know if any of you have a possible explanation, because I don't.
So what's the problem? Sorry, that somebody's getting like a vanishing spectrum from the beginning, or?
Yes, exactly. I think. I mean, Ricardo, you can ask the question live if you want. I think the problem is that the spectrum is 0 for each mode, for all modes, even under the cutoff of the fluctuation.
Yes, exactly. I get 0 values for the spectrum for each time and for each mode since the beginning of the simulation, and I
no, but
how.
Okay. So even for the first spectra you get all 0 in the spectrum.
Sorry, for the mean values, what
Yes.
do you get? Do you get them non-zero, different than 0?
Yeah, the average field is non-zero.
Okay, so somehow the code is the average, and the variances, have you plot variances, for instance?
Is, for example, the fourth column of the average scalar. If you plot that. Maybe...
Oh, I have to check.
Okay.
Yeah, check that, because the feeling is somehow you are simply not outputting the spectra for some reason, you know. I mean, it's not being written down for some reason.
Maybe you can plot here.
So just to confirm, you see the zeros in the text file, right? Not in the Mathematica.
Ricardo, you mean?
Yes. Ricardo, yeah.
Yeah, okay, sorry. I'll check and I'll let you know later. So if you want to continue, sorry.
Yep.
Okay,
sure.
Great, thank you.
Maybe I just plot here the variance as well of this. This is the variance. Okay. Yeah, maybe you should check that. Okay. No. So another thing. Okay, so now, if there is not any question, maybe I can just show you what would happen if I actually now consider the other field. So here, let me put, I use Q equal 100, the resonance parameter, and maybe you can know from this value and from your choice of omega star and F star what should be G, but for the case of the in program variables, this is a nice variable to work on, which is the resonance parameter. And basically, what we will see now is, again, for example, if I plot the inflaton field amplitude, the average amplitude, we will see again the same kind of oscillations for the first ones. At this point, nothing has happened, but if I show you the conformal field amplitude, you will see that the back reaction in this case happens way earlier than the previous case, because now we are exciting the Doppler field with a greater resonance parameter. So if you would like to, maybe the previous case of the inflaton field alone, that's equivalent of having a Doppler field with a resonance parameter equal to 3, which is particular for the case of lambda phi to the 4. But in this case, I am coupling the inflaton to a Doppler field with a larger resonance parameter. So that means that the initial band of excitation will be larger in momentum. It will excite a larger amount of modes. And also, the back reaction will happen way earlier than in the previous case. As you can see here, the decrease of the conformal field amplitude happens already before 100 time units. And it happens in a very smooth way here. So for example, if you want to characterize this, you can consider this as the back reaction time. We can also check again at the root mean square of the inflaton field, how it grows. So this is now due to the back reaction of the Doppler field into the inflaton field, and not just the self interaction of the inflaton field with itself. Now I can show you, for example, the field amplitude of the Doppler field. So it initially starts with 0 homogeneous amplitude, and on top of that we set the fluctuation. So that's why in average initially 0, and then as it grows, because it grows the initial realization of the Doppler field is random. The field amplitude will also behave random here. So this is something we shouldn't care much about. It's just because it's random, the initial condition. The same for the conformal field amplitude. But something that matters to us is, for example, the root mean square of the Doppler field and how it grows. As you can see, there is these spikes. And for the case of parametric resonance, due to the phi square, chi-square coupling, it grows whenever the inflaton crosses 0. So that's why these spikes here. You can see, and you can see how it grows, and then at some point it just goes to a steady state. It stabilizes when it has been enough exchange of energy between the inflaton field and the Doppler field. And that's something that we will see here when plotting the energies. So now I have more lines here because I have more fields, of course. So for example, again, we have in blue and in green, the kinetic and the potential energy of the inflaton dominating it initially. So we see that then there is a decrease of these two energies when the kinetic energy of the Doppler field in red, which is below the purple line, and the interaction term has grown enough that it actually back react into the inflaton. And that's why it decreases, because now the energy are comparable between them. And then, like behind them, we have the gradient energy of the inflaton growing. And this is a hint that now it has happened, like the creation of the Doppler fields now are enough to back react into the inflaton field itself. And this will lead to the growth of the gradient field of the gradient energy of the inflaton field. And this is why it grows later. And then all of these energies then go to a steady state when you can see, for example, the kinetic energy of the inflaton, the gradient energy of the inflaton, kinetic and gradient of the other field are basically in the same level. And this, we have reached to a equipartition of energy. And then, for example, from this, we can know that nothing will happen anymore, and we can stop our simulation at this point. Of course, I went, as you may have seen here, I went all the way to 2000, but at least for this case, just stopping at 300 was fine. But you don't know this a priori, so you just let your simulation run long enough. And then I can show you, for example, again, the plots of the power spectrum. For example, this is the case of the inflaton. Now, we see that the nice spikes that we were having in the previous case are not happening anymore. And now it is more noisy, but at the end, all the power spectrums tend to look like this. It goes to a peak here at some scale, and then it falls exponentially in the UV. If I do the same for the occupation number, we can see the same.
Nico, one comment. Do you have the data loaded in your Mathematica right now that you could do a zoom in?
Yeah, I can, for example, yes.
Can you do a zoom in the last stages of this spectrum you are showing, just to really show that this is a peak, so people will see it much better?
Okay, so I will maybe between 5 and 20, for example. I have it here.
By the way, I think we are officially in the coffee break, at least in terms of timing. So please feel free to go to stretch your legs, go for a coffee, etc. We'll be back at 11 a.m. Back in Europe, 2:30 in India, 5 p.m. in China. And of course, we'll be happy to stick here for a while to address questions. Could you select maybe the last times, Nico, only the last ones?
I can choose just the last one.
I mean, the density is super high. Like, can you change to a lower density of exactly? Even less, I would say. Yeah, there you go.
So the last one will be this here.
But don't cut it. I don't know why you cut it in the X range. Zoom in is only in the Y axis in this case.
Okay, so I just leave all the.
Yeah.
It was like this.
Good, thanks. Yeah. Okay, so here I think it's very visible.
Just. So that's the last spectra, the blue one.
That you see the spectra have a peak around 8, 9-ish in these units, although it sustains still a large infrared tail, you know, which ideally, if you could separate larger the scales, you would want the tail to fall off, you know, more deep into the infrared. But with this separation of scales, Nico, what do you do? 128 here?
Yes, it's 128. Yeah.
With this separation of scales and this choice of UV, it seems not to be enough to extend the tail in the infrared. But important that you see that the spectrum is dominated by a peak in the intermediate scales that you capture in your lattice. Okay, there are other questions in the chat, Nico.
Yes. The variance of the field is not 0. The model I'm compiling is a model with a cosine term potential. So you get a cosine.
Yeah, I think somehow Ricardo, yeah, we don't know why it's outputting 0. You know, it shouldn't be the case. You know, but I wonder if it's not the same problem that is given
so maybe,
negative mass squares initially. But that should
because yeah, if you say from the initial spectra,
but even if the initial conditions are not correct, this shouldn't. I mean,
it shouldn't be 0 exactly, right?
It's very strange that it's given 0. You know,
I think this is the kind of problem that we need to share to see the screen, because it's not obvious.
Yeah. So if you don't mind, Ricardo, let's postpone this discussion of your problem for the afternoon session. You know, after the last lecture of the day, and you share a screen, and hopefully we can figure out what's going on. You know, because like this is impossible.
Yeah, sure.
Looking at your screen.
Yeah, sure. Thank you.
Thanks.
There were other comments from Devika. No, it's a direct comment to me. She's asking about the mathematical file that you are showing, Nico. Can we upload?
It's the same as Paco, yeah.
It's the same upload in the practice of Paco yesterday. Okay, so you have it already.
I see. I just upload a different. It's the same that Paco used yesterday, yes. But I can upload it also.
No, if it's the same, I mean, unless there is.
Well, it's the same most of it, but I choose to plot the spectra in a different way.
Okay.
So maybe if they want to use that, we can upload this. Okay. So I plot the spectra in a different way, as Paco does in his.
Well, pass it to me and I can upload it, of course.
Okay, so I will do that. So yeah, tomorrow we're having another practice session actually, and we will actually use the same. So it will work for both.
Very good. There's another question from Alejandro.
Hi, can you hear me?
Hey, hi.
Yeah, hi, Nico. How are you? Very nice question. At some point, you mentioned that you introduced some line in your code to save the output in a different folder. Can you show again that? Because otherwise, I assume that it's just smashing what I did for the previous model.
Yes. It overwrites the previous files.
All right, and how can I?
If you want to, so I am showing the parameters file, and in the output, you will choose which folder you want your output to go.
Okay. And I don't have to write anything in the terminal, just from the input file.
No, yeah. In the terminal, you will just call your input file, and it will know from there.
Okay. Thanks very much.
Just to complement your answer, you can indeed change the input given parameter from the terminal. When you call when you call the executable, you just need to, if you add a parameter there in the line, this will override what is in the input file. So you don't even need to change the parameter. You don't even need to manage several input files.
Okay.
So you can just have one and override the parameters you want from the terminal. So that, I mean, you must choose the best way for you.
Okay.
The most convenient way for you.
Check the manual for this, Alejandro. It's very clear.
Okay.
In this, how to overwrite these parameters as Pacucina. It's very practical when you only change one parameter, you know, or one aspect of the input file. Yeah.
And also, I think there is one parameter that it's called append to files. When you actually want to like restart the simulation and you don't want to override what it's done, but actually just to start putting the output at the bottom of your files, that's append to file, but everything is in the manual.
Okay,
So,
okay, I will check
this or ask me directly at some point.
Okay, perfect. Thanks very much.
Yeah, sure. Okay, so I don't know. I can stop sharing for the meantime, maybe, or
yes. I mean, we are in the coffee break, so unless somebody has an explicit question about,
I mean, I stop sharing for the meantime, and then I will stay here.
I think you should take a break, right? Because you have the next lecture.
Yes, I'll stay here, but I just wanted to check the email. That's why.
I stop recording. Please remind me to start.
Okay.
Back, see you now. That's how.
Sure.